Today we're going to talk about the central limit theorem, which says that if we take a population with mean mu and standard deviation sigma, and then we look at samples from this population, so we take a sample of size n and we compute its mean, call it x bar, and then we take another sample of size n and we compute its mean, x bar, and then maybe another sample of size n and compute its mean, and we do this for very many samples. And in general, these should be random samples. And when we take the means of all of these samples, well, these sample means form their own distribution called the sampling distribution of x bar. And the mean we call mu sub x bar, and the standard deviation we call sigma sub x bar. And the central limit theorem says two things. The first says that if the original distribution of x values is normal, well, then this new sampling distribution, which we've created, is also normal, and it has mean mu sub x bar, which is just equal to the original population mean, and its standard deviation is computed as we take the sample, or rather the population standard deviation sigma, and what we do is we divide by the square root of n, where n here is our sample size. Now, if the original distribution of x value, so our very original population, if it's normally distributed, well, we said that our sampling distribution is also normally distributed, and this is true for any sample size. Now, if the original distribution is not normal, so this is the second part of our central limit theorem, if the original distribution is not normal, well, then the sampling distribution of x values is only approximately normal. And the larger the sample size, the more normal it's going to be. And in general, we want our sample size to be at least 30. If it's at least 30, then we can use our central limit theorem. And our mean and standard deviation is computed the same way as before. The mean for the sampling distribution is the same as the population mean, mu, and the standard deviation for our sampling distribution is computed as our population standard deviation divided by the square root of n. Now, there's a couple of things we want to note about this. First of all, the larger the sample size, the smaller our standard deviation is going to be. So if we have a large sample size, well, notice the standard deviation, when n is large, what happens to this fraction? It gets smaller. And so when the sample size is large, a smaller standard deviation means that our mean values, x bar values, are going to be closer to the population mean. And if our sample size is smaller, like over here, well, then that means that our standard deviation is actually larger, and then our sample means, x bar, are going to be more spread out. Now, another thing we want to discuss is finding the z-scores for our sampling distribution, because this is how we're going to compute our probabilities and areas and so forth. So let's take a look at the formula for the z-score. Now, in the past, we said our formula for z-score, the z-score of x, is x minus the mean mu divided by the standard deviation sigma. Now, in terms of our sampling distribution, so to find z sub x bar, well, we take our x bar value, we subtract the mean of the sampling distribution, so that's mu sub x bar, and then we divide by the standard deviation of our sampling distribution, so sigma sub x bar. And this is one way to compute the z-score. And notice this here is using our sampling distribution mean and standard deviation. There's also a way where we can use the population mean and standard deviation, right? So let's just recall, remember mu sub x bar, that's just the same as the population mean. We saw that in the previous page. And sigma sub x bar is equal to the population standard deviation divided by the square root of n. Right? We saw that in the previous page. So now if we just plug these into our z-score formula, what we're going to get is x bar minus mu, because that's just the same as mu sub x bar, and then divided by sigma over the square root of n. And now what we have here is a fraction within a fraction. Let's simplify this a little bit. So in order to simplify, I'm going to leave my numerator the same, so x bar minus mu. And now instead of dividing by this fraction down here, I'm going to multiply by its reciprocal, which is the square root of n divided by sigma. And if we simplify this further, what we end up with is x bar minus mu times the square root of n divided by sigma. And here, this is a formula for finding the z-score, and this formula involves our population mean and standard deviation. And so either one of these formulas will work, either the one involving the population mean and standard deviation, or the one involving the sampling distribution mean and standard deviation. You can choose either method. So let's take a look at an example. So in our example, we have a population of basketball players, and their heights are normally distributed. And the mean height is 76 inches, and the standard deviation is 2.9 inches. Now we're going to find the probability that a player selected at random is less than 75 inches tall. So we want to find the probability that our player X is less than 75 inches tall. And notice this is just one player, not a sample of players. So the way we're going to find this probability is similar to how we were doing in the previous assignment, assignment 10. So first thing we need to do is find the z-score. So z sub 75 is 75 minus the mean. Oh, and let's go ahead and write down our information here. Our population mean is 76, and our standard deviation is 2.9. So when we plug into our z-score formula, we'll get 75 minus 76 divided by 2.9, and this comes out to negative 1 over 2.9, which if you plug into a calculator, I believe that comes out to approximately negative 0.34. And so that means that the probability that x is less than 75 is equivalent to the probability that z is less than negative 0.34. And then we can look at our standard normal table, which I put a little excerpt of it down here, and we can see that the probability that z is less than negative 0.34, that's this guy here, 0.3632. All right, for part B, now we're saying that samples of size 25 are drawn, and the first thing we're going to do is find the mean and standard deviation of this sampling distribution. So let's start with the mean. Oh yeah, and mu sub x bar, that's the same as the population mean, which we know is 76 inches. And to find the standard deviation, let's see, sigma sub x bar, that's going to be our population standard deviation divided by the square root of n. Notice here our sample size is 25, so n is equal to 25. So we're going to get, let's see, sigma is 2.9 divided by the square root of 25. That gives us 2.9 divided by 5, which comes out to 0.58, 0.58 inches. And so there's our standard deviation. Okay, now let's find the probability that a random sample of 25 players have a mean height that is less than 75 inches. So we are going to find the probability that our mean height, x bar, is less than 75 inches. Okay. Now, before we do this computation, one thing I want to point out is that we're using the central limit theorem here. And in order to use it, remember our sample sizes should be greater than or equal to 30, which in this case, our sample size is only 25. However, our original distribution is normal, right? And if the original distribution is normal, then it doesn't matter the sample size. The sampling distribution will always be normal in this case. Okay, so we still get to use the central limit theorem. All right, so let's find this probability. And what we need to do is compute the z-score. So again, to compute our z-score, we have kind of two methods. We can either do x bar minus mu sub x bar over sigma sub x bar. And if we plug in our numbers, we'll get, let's see, the x bar value we're interested in here is 75, minus mu sub x bar, which is still 76, we got that from up here, divided by the standard deviation, which is 0.58. And if we plug this into a calculator, well, let's see, this comes out to -1 over 0.58, which is then approximately -1.72. Right. Remember our other method, if we want to use our population mean and standard deviation, then what we're going to get is x bar minus the population mean times the square root of n all over the population standard deviation. And if we plug in our numbers, we'll get, let's see, 75 minus 76 times the square root of 25 all over our population standard deviation, that was this guy here, 2.9. And so what does this give us? Let's see, in the numerator we have 75 minus 76 is -1, times the square root of 25 is 5, so -5 over 2.9. And if you plug this into your calculator, you should get approximately -1.72. So either way, you should get this same exact z-score. Okay, so to finish our problem, the probability that x bar is less than 75 is equal to the probability that z is less than -1.72. And then if we look at our table, we can see that this probability is 0.0427, and that would be our answer. Notice the probability that a sample of 25 players has a height less than 75 inches is much smaller than the probability that just one player selected at random has a height of less than 75 inches. And there we go.